one and all present here. It's certainly an enriching FDP to attend. So, with me being a participant as well, it was certainly enriching yesterday, and I'm looking forward to more days to come as well. So, it's my happy pleasure to introduce our first speaker for the day, Dr. Vivek Patel. He has also been a former senior to me at PDU, so I do even have some pleasant memories with him. Dr. Patel is currently serving as an associate professor in the Department of Mechanical Engineering at University of West Trollhättan, Sweden. Dr. Patel completed his PhD in material science from Pandit Deendayal Petroleum University, Gandhinagar, India, in February 2017, with his thesis focusing on experimental investigation on friction stir processed AA7075. His research expertise spans across several advanced areas, including friction stir welding and processing, ultrasonic welding, solid state additive manufacturing, advanced materials characterization, light metals, particularly aluminum and magnesium, dissimilar welding techniques. Dr. Patel has been instrumental in advancing robotics friction stir welding of aluminum alloys through collaboration with Swedish industries and projects funded by national agencies. With over 11 years of teaching and research experience, Dr. Patel has played a key role in developing undergraduate and master's courses and supervising students at bachelor's, master's, and doctoral levels. He has published over 40 SCI journal papers and 6 book chapters with more than 2,500 citations in the area of friction stir and fusion welding processes. He also serves as a reviewer for more than 35 SCI journals. Today, he will be sharing insights and expertise with us. He will be speaking on the topic friction stir welding, a sustainable manufacturing technique, highlighting the potential of this innovative method to promote sustainability in manufacturing processes. So, please join me in welcoming Dr. Patel. Vivek, sir, over to you.
Sir, just one humble request to all the delegates. Can you all switch on your camera so that we can have one common photograph? Dharmik, are you there?
Yes, sir.
I request all of you to please switch on your cameras.
Actually, sir, I'm trying to open my camera, but it does not allow me. Why? Hello.
You're audible, Vivek.
Yes, but I'm not able to have the access to my camera, so I'm struggling.
Sir, you were visible, sir.
Okay, perfect then.
Yeah. Yes, sir. Yeah, you're visible, sir.
Okay, okay. Yeah.
Dharmik, have you taken some common photographs?
Yes, it is there.
Can we move on?
Hello. Yes, sir. Yes.
Okay, thank you. Yes, sir. Vivek, sir, please continue, sir. You can
Yes.
share your screen, sir.
Just a second. Okay. And I will share. So can you see the presentation more?
We can see your teams, sir, not the presentation, sir.
Uh-huh. Just to give me a second. Now can you see my screen?
Yes, sir, it's
Yes, sir, it
visible.
is
Yes.
visible.
I have to remove this one, right? Yeah, so shall I start, sir?
Please, sir, please.
Yeah. So thank you for uh, this opportunity, and I will try to talk about friction stir welding. And I think I should be talking for 1 hour, right, sir? Or what is the time limit?
Yes, sir, you can, maybe 1 hour, 15 minutes is also fine. Yes, sir.
Yeah, thank you. Yeah, so uh, first I will give you some brief introductions from where I come now. So uh, I come from University West uh, in Sweden, and we are located near to the second largest city of Sweden, that is Gothenburg. And when it comes to the educations for the university, then we deal with all cycles of education starting from the bachelor, and we have some programs, mechanical, automations, and industrial engineering. And also we have some programs at second cycle of education, that is a master's. And we deal with mainly manufacturing, welding, and robotics. And for artificial intelligence and automations, that these are the recent programs we started in last couple of years. And also we provide PhD educations, that is the last cycle of education, and we do some industry-driven research in our research environment. So what we do here in terms of research, so our research environment named Production Technology Center, and we work on three corners of a triangle. One is a material science, then manufacturing processes, and some physics of the process by using softwares and some simulation tools. When it comes to the material science, then we are largely involved in superalloys, nickel-based and titanium alloys for a lot of engine materials. Also, we work with the steel, especially high strength and low alloy steels with duplex stainless steel. And also we work with some light metals of aluminum, cast aluminum and wrought aluminum alloys for various applications, and also some applications of magnesium and copper alloys. When it comes to the process, manufacturing process, then we largely cover all manufacturing processes for joinings in welding, and also we do substantial amount of research in additive manufacturing when it comes to DED, wire-based especially, and powder-based fusion. So we work in a wire arc as well as a laser source for additive manufacturing. And we have some other departments, thermal spray, non-destructive testing, and robotics and automation. In comes to division of welding from where I come. So these are the infrastructure for the welding processes. And also we do in-house material testing through mechanical properties and microstructure correlations. So that was the introductions, and let's try to begin today's session. So before we go to the friction stir welding, then I would like to start with the welding. So as you can see on left of the screen here, then I think everyone you know what is welding. So basically welding is nothing but joining of two or more than two components together. And here we apply the heat source to the joint where we want to have the combination of more than one material. And there are several joint configurations are possible, maybe more than this, but I try to put basic joint configurations, especially for structural applications. And I just put a classical example of automotive industries where welding stands and what are the applications when it comes to the welding. So as you can see in the right corner bottom of the screen that the several joining methods being followed by assembly of uh, commercial automotive vehicle. So you see the fusion joining. So that's laser welding, arc welding. In arc welding, it's a lot of applications by MIG and TIG. Then mechanical joining. So you have a lot of fasteners, then rivetings, then hybrid joining, some chemical joining, and solid state joining over here. That's what we are going to talk today. And if we see the solid state joining, then gradually now the solid state welding is replacing some of the joining techniques in automotive industries, and especially now the entire automotive industry is going to shift toward electrification. So we all know that how big electric vehicles are crucial for future. So there are a lot of applications of friction stir welding when it comes to the electric vehicles, whether it's a fully electric or hybrid, but there are significant share of friction stir welding now we see, and we work for a process development for OEM, auto means original equipment manufacturers. So to see the evolutions of friction stir welding, uh, uh, it's not quite old welding technique like the rest of the fusion techniques. It's a quite new technique invented in late 2000, and it got patented for 20 years. And few years back, the patent has been expired, so the patents is no more valid. So there are a lot of companies are trying to exploit now this technology for different applications. And when we talk about the scientific publications, what has been done so far in friction stir welding, so we see thousands of publications and several patents are available now. And if you see the trend, I try to fetch the trend before 1 year based on Scopus data, and you can see that the number of publications are significantly increasing. So there is a lot more happening in friction stir welding, and the graph is quite exponential growing. And if we see the status of research in which domain, so you see here mainly engineering and material science. So there is a lot of research is happening and a lot of funding has been raised for lifting the TRL for this technology. Then this technique was invented and the initial application for welding the high strength aluminum for some aerospace applications. And these high strength aluminum alloys mainly includes aluminum 2000 and 7000 series, which are normally not weldable by fusion route. So these materials have certain, I would say, tendency towards hot cracking when you try to weld by fusion methods. So initially, this method was ideal for aerospace applications. Those use high strength aluminum alloys. But now we see in the last couple of years and for next 5 years or 10 years period of time, there is a lot of push for this friction stir welding for e-mobility for electric vehicles. So we see significant push for this technology for joining different applications of automotive industries. And the automotive industries are willing to accept because now the ISO standard is available when it comes to the process qualification. So the ISO standard recently published with two revisions, and that allows companies to implement this technology so they can qualify the process based on ISO standard. So this is how the process has evolved so far. Now, what is friction stir welding? So the friction stir welding is a solid state process. So here there is no fusion of material. So you don't melt the material basically. And if I can run this video, let's see, yeah. Then you can see in this process, you have the tool and the tool is rotated and the tool is plunged to the workpiece where you want to weld. And then after the inner fit is applied, then you move the tool in the directions of the welding in 1 dimensions, 2 dimensions, or 3 dimensions, depends on the component. So we don't see any fuel and we don't need any filler material. You don't need any shielding gas when it comes to the welding of aluminum. So basically, it's a clean process. You don't need a surface preparation also. So if we categorize this welding process, so solid state, so you work less than 90% of the melting point of the material, and the energy source is completely mechanical force. So you apply a significant amount of force downward, and the force varies from material to material and from thickness to thickness, what you want to weld. And the source, heat source or thermal source is nothing but the friction between this tool and the workpiece. And the mechanical loading is the pressures applied by this tool surface, the probe and the shoulder that we will see in the next slide. And the shielding is not mandatory, especially for aluminum alloys. So I would say you save a lot of resource when it comes to the mass production. So let's try to understand with some basic illustration of the process. So the friction stir welding, the working principle is understood by 4 steps. But before we go to the 4 steps, let's try to understand what you need if you want to do a friction stir welding. So first, you need the backing bar or significant amount of rigid support. You can see that's nothing but the table, or I would say the backing bar you need. And the second thing is a tool. And the tool is nothing but the heart of the process. And you see the tool that the tool has a shoulder. So shoulder is nothing but the larger diameter, and the probe is nothing but the smaller diameter. And this tool basically is driven through the rotational energy. You can see clockwise or anti-clockwise, depends. And then after this is the example of the butt joints. So you have one part and the second part, and these parts to be welded. So the first step is that the plunging. So the tool makes the contact to the workpiece and you wait the certain time. So that's called dwelling. And the dwelling time basically depends on what temperature you want to weld. So once the temperature is reached, then you will start taking off this tool in the welding direction. So second step is a welding. So the tool is take off in a welding path. And while the tool is moving, then you see that this surface is developed, and this surface is nothing but the footprint of the bigger diameter of the tool, that is your shoulder. And the footprint of the smaller diameter that cannot be seen from the naked eyes here. So for that, it is visible in the cross section of the weld. And then after the fourth step is a dwelling or retracting. So you can see that you end up with the keyhole. And if you see the process parameters, how the process is controlled or governed. So once you have the right dimension of the tool, then the process temperature, or I would say the heat input, is controlled by these three red arrows. The first one is a rotational speed. So higher the rotation speed, more the friction, so you generate more heat. Downward force, so the amount of downward force basically will decide the surface quality on the weld surface. So if you have less amount of downward force, then you can have some cold defects, or maybe you can end up with a probe failure. So downward force also very important to decide the right process parameters. And the last is the welding speed, and the welding speed provides the production volume or productivity. And welding speed is very crucial when we talk about the automotive industries, where production volume, they count on a fingertip 24/7. So by playing these three variables, basically you can decide the right weld surface and the weld performance by detailed testing and characterizations. Now, next question. When it comes to the material, then what materials friction stir welding can weld? So the materials, so the most metals can be welded by friction stir welding, and we start with the aluminum. So there are significant evidence of aluminum. So all the aluminum alloys, starting from the pure aluminum to the highest strength aluminum, you can weld by friction stir welding. And luckily, we have the ISO standard for aluminum friction stir welding. So there is no doubt for putting to the production and running the components, whether in the lab or on road, in shipbuilding or aerospace. Magnesium also, it's quite evidence. We find a lot of research articles and a lot of space applications now where magnesium alloys are welded by friction stir. Copper, of course, it is a mature for copper also. But for welding of copper, the tool material plays a significant role. So you should have a different tool material when you are welding aluminum and copper. And steel and titanium, I would say this is the new topic or new materials being investigated right now in friction stir welding. And these two materials basically are hard material compared to the top three material. And because of hard material, the tool material needs to be even more harder. So now there is a significant advancement on the tool material for welding steel and titanium, and it looks promising, and we will see the friction stir welding of steel and titanium just like what is happening in aluminum and magnesium at the moment. Then when it comes to the dissimilar combinations, then due to solid state nature, this process provides a lot of freedom to weld dissimilar combinations. So you can see that you can weld varieties of the dissimilar combinations. So that makes designing of your product or component much more flexible when you want to compensate the weight or density of the structure. So that's a good choice. And also when it comes to the the processing route. So friction stir welding can weld cast material and sheet metals, extrusions. So there is no problem what is the source of the material, because we know that to weld a cast material, it's always challenging when you go through the fusion routes, either arc or laser source, because cast material always has a traditional porosities and the shrinkage cavities and the defects, and that becomes more challenging when you melt during the fusion welding. So the casting basically welding cast alloys, I think it's no issue in a friction stir welding. Then joint configuration. So friction stir welding can allow all the butt welds, all different types of butt welds, and also lap joints. And in lap joints, you can have the multiple lap joints. So that is the beauty of this process. So you can have the multiple sheets, 1, 2, 3, 4, 5 on top of each other, and you can pass the tool and you can build all the sheets or plates together in a one welding pass, which is quite difficult by the fusion method. And of course, nowadays, because of the fixtures and the tooling, the T-lap joint also are possible. So it can take care of different weld configurations. So that provides also a lot of freedom to the designer for designing the component. Then, yes, every process, manufacturing process has a defect. So, but it's all about how you can tackle, minimize, and eliminate those defects. So in friction stir welding, the defects that you can see from the naked eyes, that's a flash on the surface. So you can see the picture, one of the example of the flashes. So you see a lot of flashes on the surface. So this is a defect, but this defect can be tackled by post-welding treatment. So you can do deburring or machining, but that is not the ideal case. So this defect basically is a result of a higher heat input condition. So we call this is a hot welding condition. On the other side, you have some tunnel on the surface that you can see from the naked eyes during the process. And you can see in this actual picture. And this could be the result of a cold defect, or I would say the cold heat input process variables. Then another defects that we can't see from the surface that we need a microscope so that you can see from the cross section. So it's a lack of penetration. You can see here. That's quite common in case of butt weld. And in case of lap joints, so you have some hooking. So hooking is like a conventional defect microstructural feature that presents in a friction stir welding when you have the lap joint. And this hooking, basically higher the hook, you lose some strength in the joint when you test from static strength or fatigue perspective. So the main focus is to try to have the minimum height of the hook so you can have the stronger joint at the end. So these two defects are only visible through microscope. So you need to have a cross section. Now, why friction stir welding in manufacturing? So what it brings to the table compared to the rest of the welding techniques. So there are certain metallurgical benefits. So solid state nature, and during the process, you do not lose any alloying elements if you are working with some alloys. Especially for those alloys, they are having more than one element. So in a fusion route, there is a significant chance that you will vaporize some of the alloying elements having the lower melting point. So here there is no loss. So all the alloying elements are intact after the weld. There is no melting. So you get rid of solidifications cracking. And due to the lower working temperature, you ends up with a minimum distortion. And due to the plastic deformation, so you get very fine recrystallized microstructure. So here you can see this is the EBSD map of 7000 grade of aluminum, 7075 T6 condition. This is a parent material, and after the weld, if you see the weld nugget, then this much amount of grain refinement you can have. So this grain refinement is happening from this elongated pancake grains of rolling to the fine aqueous grains, and this is nothing but because of the plastic deformations. So here there is a severe plastic deformation is happening during the process, and that gives you the fine structure. And this fine structure basically helps to gain some properties in the nugget. And ultimately you have the stronger joint. So that fine structure contributes to the mechanical properties. So when we talk about the mechanical properties at room temperature in a static way, the static tensile strength, then the joint always fail either from the heat affected zone or from the parent material itself. So this process gives almost 90 to 95% of joint strength. So in terms of mechanical properties, friction stir welding guarantees better strength compared to the fusion joining methods. Also, along with metallurgical benefits, it has several environmental benefits. And that's why we call this process is more sustainable compared to the fusion methods. And when we talk about the sustainability, then here in the process, if you take an example of welding of aluminum, then you don't need a shielding gas. So you save a lot of gas. Basically, it's very expensive also, and also that creates a lot of harmful emissions. So you get rid of all these issues related to the shielding gas and the emissions. Also, you don't need a filler material, so also you save a lot of resources. And if you have the right process parameters, right tooling, then you can eliminate the heat treatment after the welding. So you can have the weld nugget almost similar to the parent material. So you don't need a heat treatment. So also here you save a lot of resources. So we call this process is quite sustainable, and that's why that's a huge demand is coming for automotive companies for uh, different applications. And also in terms of power, friction stir welding consumes less power, very, very less power compared to the fusion welding. So in the average of maybe 50 to 70% less power is used by friction stir welding when we compare with the TIG or MIG welding. In summary, so I try to put summaries that the green and clean process, low distortion, superior joint quality. Then you can minimize the heat treatment in most of the cases. And this is one of the important applications that now it's addressing a different applications that is a leak proof. So friction stir welding provides a leak proof guarantee, I would say, when you are going to weld cast aluminum alloys. So due to that characteristic, there are several applications to build or develop different heat exchangers made of aluminum and copper, heating and cooling plates. So a lot of heat transfer or heat management devices are being investigated to weld by friction stir welding now. Then it endorses several dissimilar combinations, which is very crucial when we talk about batteries. So aluminum to copper, I think one of the target, pure aluminum and pure copper in a battery cells. So it's a prominent way to weld as compared to the laser welding at the moment. And yes, it's a sustainable welding process. But every coin has a two side. So I try to list here some of the, I would say the challenge or some research questions based on the limitation of the process. So this process gives exit hole. When you take out the tool after the welding, then you end up with the keyhole. So that exit hole. But there are several ways now to deal with the exit hole. So uh, you can avoid the exit hole in a component, real component itself. Yes, one of the applications which restricts the friction stir welding, that you need a backing bar. So once you have the design where you don't have enough support for a component, then friction stir welding does not come to the picture, where laser welding comes into the picture. So it's up to the designing stage whether you would consider this process. Then you have the provision for some support to have the backing bar. But another thing that's possible to use a different tooling system in terms of bobbing tool to get rid of backing bar. Then the tool materials. So friction stir welding is so far limited to weld light metals and I would say lower strength alloys like aluminum, magnesium, and copper. But it's not so much investigated or uh, implemented for welding of steel, titanium, and maybe in future super alloys. And that because of the tool material. So here the tool materials should be uh, even higher than the strength of the workpiece to be welded. But there are certain companies, they are working on developing the new tool materials, quite hard tool materials, and that can be used to weld the steel and titanium. And yes, low flexibility in joint configuration. So you need a backing bar or support. So it gives a little bit less flexibility when it comes to the joint configuration. So the applications. So I try to put the different applications in friction stir welding, starting from electronic side, then aerospace, shipbuilding, automotives, and railway industries. So let's start with electronics. So in electronics now, friction stir welding being used for developing the enclosures for the circuits, and especially for electric vehicles. So the friction stir welding is quite prominent to make a thermal management system or cooling plates. So you can see here some pictures of the cooling plates for one of the electric vehicle component. And in, I think, almost 12 years ago, the friction stir welding was introduced to welding MacBook of aluminum panel. So that was one of the applications that investigated and implemented to weld the back and the front panel of a MacBook to make it more lightweight and robust. Then aerospace. So in aerospace, that's a number of applications, but I try to put a couple of applications of fuselage and wing structure and some fuel tanks. So this propeller tank, like hydrogen tank, and you can see the weld track of friction stir welding. So that's applications by European Space Agency, ESA. And some rocket structure, you can see some weld tracks of friction stir welding on high strength aluminum alloys. And there's a recent application in NASA, this orbital welding of big structure of one of the spacecraft called Orion. Shipbuilding, yes, in shipbuilding, it's quite a large share this technology has. And it starts with the lightweight panels of aluminiums in decks and floors of any ship or ferries. And you can see this, whatever you can see, these lines are nothing but the friction stir weld lines on there's a big bow section of a US Navy vehicle. Then also you can see this is the floor panels, extrusion floor panels of one of the marine applications being welded right now. And yeah, some more applications of US Navy also. So in shipbuilding also, marine structure, a lot of bridge and some of the offshore applications, friction stir welding of non-heat treatable aluminum grades of 5000s are popular. Then for automotives, some of the applications you can see here. So Honda demonstrated a successful welding of aluminum and the steel in a chassis. Then some Taylor welded blank having a different thickness of aluminum of high strength. You can see here uh, the weld track over here. Then some of the Volvo wheel assembly a long time back. And some welds of a space frame of Ford. A few examples. Then for railways, for trains, and especially for high-speed train, the friction stir welding quite popular candidate for joining methods. And you can see these are the extrusion panels of the, the train body, and you can see number of weld tracks by friction stir welding. Now, I will try to give you more insights on friction stir welding, and I will try to put some of the uh, methods what we are following at University West and what we are doing in terms of novelty and helping the companies nearby Sweden. So this is the state-of-art system we have. This is the 5-axis robotic system for friction stir welding. So it's a ABB system installed by ASAB in 2010 or 2011, long time back. And it has 5 axes, so we can do a different 2 dimensions welding for prototypes development. So what we have done so far, so a few PhD graduates have developed the temperature and the force control robotic system. So basically we have developed a system that can be controlled through a temperature. So what we do, we control this process through temperature measurements, where you can see that we don't insert the thermocouple to the workpiece. Rather inserting a thermocouple, one end of the thermocouple is fixed always on the back of the tool, and the other thermocouple is fixed on the one of the contact point of the workpiece. So when the tool makes a contact, then the circuit is complete, and that circuit is complete, and we measure the voltage, and that voltage basically changes when the temperature is changed. And this temperature change depends on type of the material of the tool and the workpiece. And that voltage difference at different temperature we calibrate as a welding temperature. So if we put the set temperature for a particular aluminum 500 degrees Celsius, then we will ensure that the welding has been done at 500 degrees Celsius, irrespective of the heat sink, irrespective of the heat geometry. So this robust system developed by the PhD graduates that will make sure that the other parameters like rotation speed, if you recall the previous slides, the process variables, 3 red arrows. So those 3 red arrows are changed to make the temperature constant. So we ensure there is no defect. Then also we do a lot of tool designing. So still I believe in friction stir welding, the key component is the tool itself. So there has to be a appropriate tool design, whether it's a shoulder diameter or shoulder features, and the probe diameter and the probe features, small tiny features makes huge difference for the material flow. So the tool design and development, I think we spend most of our time for particular process development. And of course, we evaluate a process after DOE through a structure property. So we do excessive microstructure and the mechanical property evaluations. And then based on that, we come to the conclusion of the right tool dimensions and the right process variables. And this is one of the topic we are working right now, how to monitor and control the process in a production environment. Because to monitor and control in lab environment, and when it comes to the production, then the things are quite different. So for next few years, we are going to work on monitoring and the control, and we will work more towards artificial intelligence and machine learning, so we can have the better control over the process. So I will show you our key findings maybe for your interest. So these are the 5 key findings I have mentioned, what we have done in last 4 years. So we try to develop process for battery trace in electric vehicles. Then we try to figure out the battery box assembly by welding cast aluminum to the wrought aluminum. So we try to work on welding of 2 different aluminum. One is a cast and one is a wrought. Then cooling plates, or I would say heat exchangers for electronic enclosures for several applications. Then aerospace applications, we are working for fuselage structure in aerospace. And also some efforts we are trying to work on bimetallic joints, for especially for aluminum to copper for bus bars, and new applications we are targeting for heat exchangers. So let's try to see what we have done in the first process development, battery trace. So all of you must be aware that how the battery tray for electric vehicle looks. So this is basically the battery tray, the entire, I would say, the box in layman language. And this box is nothing but the engine of electric car or electric truck. And this box basically is filled by a lot of battery cells and battery modules. So the key challenge is that how to make this battery structure leak proof and have the strong joints. So why friction stir welding? So the automotive companies, basically it's a clean and green process. So that's the answer that why they should go for friction stir welding. Second is a leak proof. So yeah, it provides a leak proof characteristic when you are going to weld the dissimilar materials. So let's say this frame, front end and the rear end is made of casting. And if you want to put a top cover of sheet metal, then it becomes tricky when you want to weld with the fusion, maybe TIG or laser welding. Then, of course, superior joint integrity because of the solid state nature. And how about the production volume? So whether friction stir welding can be pushed to the limit of laser welding. So can it be approached more than 2 meters per minute? So your tool can move more than 2 meters per minute. So it can compete laser welding. So that was the questions we tried to answer during 2020 to 2022. So we tried to push the limit. And in that work, we tried to form the objective that let's try to push the friction stir welding up to 5 meters per minute for extrusion aluminum alloys of 6,000 grades. And this is how the floor panel looks. So these are nothing but the extrusion floor panels for cooling purpose of battery cells. And you need to weld as a butt joint when it comes to the assembly. So in that process, we try to work on a different tool design so that tool can work at high welding speed for 5 meters per minute. Because for high speed friction stir welding, the main challenge that the tool should survive. So there are high chance that this probe, the smaller diameter, can break from the shoulder, the bigger diameter. So We tried, and after optimizations, we found that 4 meter per minute welding speed gives a reasonable good joint, and that qualify as per the ISO standard of friction stir welding. So you can thank you. So you can see the weld surface, and the weld surface we almost try to manage this butt joint that without any flashes. And when we check this cross section of 3 millimeter thick plate, then you can see there is no lack of penetration, there is no defect. So the weld cross section provides promising uh, data as a result of tool and the right parameters. You can see the parameters, and when we see the factography after tensile test, then weld failed from the heat affected zone. Initially, during the tensile testing, it tried to open from the root. You can see some void during the tensile testing, but ultimately it failed from the heat affected zone, having around 75% joint strength. Then also we try to understand whether high speed weld are same like a conventional welding speed of friction stir welding up to 1 meter per minute or 2 meter per minute. So we try to uh, see the microstructure through SEM, and we found that the stir zone basically due to the severe plastic deformations, because the parameter we used, that parameters was so much aggressive, more than 3000 rpm, and around 8 kilonewton downward force. So that created a lot of plastic deformation and plastic strain to the wheel nugget, and that allows that the grain size reductions up to 7 micron from 50 microns parent material. And also we found that in a failed specimen after tensile testing, the grains of stir zone was quite uh, shown some elasticity. So you can see elongations in a well nugget itself when the plastic deformation is happening. So so far we have pushed the limit up to 6 meter per minute, but so far we got the right properties at 4 meter per minute. And then after you see this is the real battery floor panels, and this is the cross section of the weld surface. And you can see that in this color metallography, that you can see these bands in the weld nugget itself. So these bands basically represents the typical onion structure of friction stir welding. So we see that this material flow is happening at such a high speed, and there is a lot more to understand and learn from these onion bands in the weld nugget. Mm. So that's, I hope you can see this video of battery floor panels welding. And also in this work, we try to work on a stationary shoulder. So that's, I would say it's a new tooling system. And in a stationary shoulder, you can see that in this schematic, only the shoulder, the bigger diameter remains non-rotating. So it just slides on the surface. And the only rotating member is a smaller diameter, and that is a probe. You can see here the probe. And the stationary shoulder provides basically the smooth surface. So you cannot have the burrs and the flash on the surface. But still there are several challenges for stationary shoulder. So there is only this probe is rotating. So it's a lot of sticking of aluminum. And as a result of sticking of aluminum inside the stationary shoulder, there is a very high chances that the probe gets broken during the welding. So there's a lot of sticking is happening. So you need frequent cleaning. So that's quite, I would say, more work to be done in case of stationary shoulder when we talk about the production. But some of the demonstrator you can see, if, let's see if I can run this stationary shoulder. So this is the video. You can see that you don't see any rotating member. So inside this stationary shoulder cover, the probe is rotating and it's creating the weld. And this is the butt joint in front of the tool, and the behind you see, you get the clean surface. So how it looks, so you see that the butt joint surface is almost like extrusion lines on the plate. And if you see the cross sections, then again you see there is no shoulder deformation on the top. So your weld nugget is completely probe dominated or probe driven. And also you see the significant onion bands as a typical friction stir welding microstructure. Then, in order to make a strong case that, okay, why this friction stir welding? So there was a small case study on a sustainability where these floor panels, extrusion floor panels, that is commonly found on all electric vehicles for cooling down the entire battery assembly, that being welded by different methods, and different welding processes were selected by different partners, and try to analyze the sustainability and try to see which process stands best in terms of sustainability. So you can see that some results that this is a base material of 6000 aluminum in T6 condition. And if we see the graph of tensile strength, then you can see that the friction stir welding is matching to the, I would say, some hybrid welding. And this laser MIG hybrid welding. So the other process also shows quite a decent tensile strength. Then also we try to understand the welding speed from a sustainability perspective. So how far you can push, so up to 3 meters per minute was a target, and you can see this laser beam welding by obvious, and you can see some of the laser MIG hybrid welding. So this LMH is nothing but combination of laser source and MIG source to make it high speed. So these three processes were competing with each other in terms of tensile strength and the welding speed. But then after try to have the quantifications of the carbon footprint. So how much carbon is emitted during the process, that you can see this comparison of electricity consumption, amount of filler materials are used. So in friction stir welding, no filler metal, no shielding gas, and also electricity consumption is quite less here. So overall, the carbon footprint was found very, very, very less compared to the rest of the welding process in terms of welding speed and the tensile joint strength performance. So the conclusion was that the friction stir welding is one of the ideal candidates that fulfills the sustainable development goals under UN redefined 17 goals, and that fulfills goal number 9, 12, 13, and 17. So that was a case study of why this process is more sustainable compared to the other methods. Then the entire battery box. So the entire battery box, how it looks. So you see that there are two big casting 1 and casting 2. These are the high pressure die casting of aluminum. Basically, it is a frame structure of any battery tray. And this battery tray is sealed by sheet metal on the top. And you can see this weld trap over this 1 meter by 1 meter. So we wanted to understand whether this sheet metal to cast aluminum can be welded in a lap joints and what are the joint integrity. So, so we optimize the process by having the sheet metal on the top and the high pressure die casting on the bottom, and you can see the typical cast structure in a weld cross section. That's a dendritic structure, and on the top you have the extruded material. And when we tested after process parameter, then in a tensile testing, you see that the weld was trying to open from retreating side. It's a typical cold lap feature of lap joints in friction stir welding. But ultimately, the final failure happened from the near to the hook side of the cast material, as expected. And then some of the videos you can see that how close we are welding. Yeah. So here on the top, you have the extruded material, and this is a cast component. And here we are welding very near to the edge in a 2 dimensions. Yeah. Yeah. Another example of cooling plates of electronic enclosures. So I tried to fetch one picture yesterday night that how these cooling plates and the heat exchangers are right now trending in industries that are the best component to be welded by friction stir. So one of the Tesla a thermal management system, you can see these wheel tracks. And this is nothing but the friction stir welding you can see is visible when you dismantle this outside edge of the thermal management system. So we have been working on the similar concept where we are welding a cast to cast, and this cast material is a special casting, and this alloy has some copper, around 2 to 3% of copper, and that is not possible to weld by fusion method, so especially laser welding, because by having laser welding aluminum with some copper, that creates a lot of stress corrosion cracking and hot cracking issues. So the ideal candidate was a friction stir welding, and you can see the cross section of this lap joint. And also in this project, we try to explore what different combinations we can have. Can we weld high pressure die casting to high pressure die casting? Then can we weld sand cast, which is even a lower grade of casting, but cheapest form of casting? Then can we weld a combination high pressure die casting to sand cast? And also we explore, is it possible to weld even a high pressure die casting to wrought alloys and so on. So we try to work on a different combinations and try to make the economic case study that what combination of material can be used. So some of the process parameters I can show you. So this is the high pressure die casting, top, bottom, same material. And this is a cross section. And when we test in a tensile, and then after if we observe the cross section, then after tensile, you see the failure happens from the parent material rather than the weld nugget. So the weld nugget is intact. So that promises that the leak-proof characteristic at a joint, basically if you want to develop any heat exchanger or cooling plates, because in cooling plates, you will have a cooling medium flowing at particular pressure, and you have to make sure that that pressure should not influence the joint. So you cannot have the accident or unwanted maintenance for different thermal management system. Then also Zencast also similar way, you can see the cross section, and we try to understand the different features of lap joints, hook and cold lap. And you see that the cast, the sand cast, basically it behaved differently. So here you see it's failing almost near to the heat affected zone, not on the weld nugget, but in some of the tensile specimens we found that it's opening from the weld nugget itself. So that's basically due to the lot of large voids and a dendritic structure of the cast material, and there is a lot more to do for sand cast when it comes to the friction stir welding. Then here we check the combination of die cast to sand cast, and you see that it's free from the sand cast. So weld nugget is intact. So it's a the final failure is happening away from the hook and on a sand cast. So some applications now for some aerospace applications. So in aerospace, you see a lot of applications, a lot of friction stir welding happening for fuselage made of aluminum, light metals, and the grades are typical 2000 and 7000 grades. So we try to have the T joints, and we wanted three sheets together for one of the applications for uh, engine component. And then I can see you means we can see the cross section. So there's a sheet material 1, material 2, and material 3 in a T joint configurations, and we wanted to build these three materials together. And after process optimizations, you see this complete full penetrations in this wall also. And we welded 2000 and 3000 in three sheets together in one welding pass. And how close this you see the interface looks. So there's a significant refinement you can see in the weld nugget to the parent material. And also we tried to map the hardness, and we know that the 2000 and 7000s are quite high strength alloys. So they possess a higher hardness and higher tensile strength compared to the other aluminum alloys. So it's important to see that where the hardness drop is coming. So we found that the weld nugget has not too much reductions in the hardness when we see the hardness of the parent material after these T3 and T76 heat treatment conditions. And as next task that we are going to investigate this for fatigue strength. Then also we worked for welding a butt joint of 7000 grit 6 millimeter thick, 6 or 6.35 exact thickness of butt joint. And that time we selected a stationary shoulder to minimize the distortion and to have the better temperature gradient from top to the bottom. So after tensile, you see that we checked and we found that the failure location happened away from the heat affected zone. And almost we got the tensile strength very similar to the parent material. So almost we got 90% of joint strength of 7000 grade of aluminum. Then the last applications for bimetallic. So this is a new activities we are doing now, and we are trying to weld aluminum on the top and copper on the bottom. That's a typical application. And one of the cross sections we can see here, that's on the top you have the aluminum, bottom is copper, and we design our own tool so that tool can effectively work on a copper side than the aluminum side, because it's always tricky to mix the copper with the aluminum because of a difference in melting point and of course the property. So here you have a lot of intermetallics as expected, and so we try to monitor the hardness at different intermetallics, and we try to understand what's happening and how this intermetallics becoming hard. So we found around 175 HV in some of the case we found 200 HV hardness against 95 HV of aluminum and copper. So it's a very, very brittle intermetallics, and these intermetallics are detrimental to the joint performance. And also you have a lot of challenges when you are transferring electric current out of those joints. So it creates a lot of obstacle to the electricity. So next task is to minimize the intermetallics and to correlate with the electric resistance at the joint interface. Then in the last stage of my presentations, I will throw some ongoing developments to you and what we are doing and what is the research questions worth to pursue in friction stir welding. So the first I will say it's a hard material. So friction stir welding of hard alloys like a steel, titanium, and a nickel-based material. So these three categories of materials are quite new, and for that there is a new tool development need to be done. So you need a very hard tool material, and not only hard tool material, but also you need to process, you need to machine down to the small features on a probe and the shoulder. So uh, that's a lot of research is happening. So you can see that Element 6 has developed a tool material to weld the steel, and it's like a new tool material. It's like a synthetic diamond in some metrics. So that you can see some recent applications of 6.3 millimeter thickness of titanium butt joint, and you can see it's a beautiful cross section of such a hard material, and you have very fine grains, of course. And if you will by fusion methods, then you have very like a columnar structure for this material. And also in a small thickness. Then that's a new technique called spot welding. So that's a refill friction stir spot welding is gaining a lot of attentions to replace rivets, fasteners, and maybe resistance spot welding in near future. So one of the recent application, you see that Lunar Tower by uh, EWI, you can see some of the applications of high strength aluminum being welded by refill spot weld. So how refill spot weld works? So rather than linear welding, you have the spots here. So let me see if I can run this video. So you can see there is a spot welder on a robotic arm, and it has a different tooling arrangement. And in different tooling arrangement, you can see that the probe is coming first, the probe is coming, but there is another sleeve which is making the spot. And when the tool is coming out, you don't have a keyhole. So I would say it's a new development, and it's ideal for replacing the riveted joints or resistance spot, and also some of the applications uh, for bimetallic joints, aluminum to copper. You can see some spot for automotives and electric connections. So that's one of the project we have started to work to with 2000 and 7000 by Refill Spot Weld in collaborations with the Sturtech Austrian company. And you can see how the spot weld looks. So there is no keyhole at all. And we are trying to develop the understanding of different defects and what's happening in the microstructure. Then some new projects. We are now friction stir welding can be substitute for TIG welding for several applications in joining of aluminum, especially for energy applications. So we have been welding this 25 millimeter thick block, and you can see this 25 millimeter thick block is welded in two directions. These are on one welding pass, and on the other side there is another welding pass, and we have completely defect-free welds of thick blocks of energy applications. Then the new topic that how to ensure there is a good quality of the weld surface. So that's what we are working, and it's a interesting topic, I think, for all manufacturing process, especially for welding processes and additive manufacturing process, that process monitoring and control. How we can develop the tool which can make sure that can give you the idea the process is correct or not. So we are trying to work on this defects capturing through online monitoring tool system. And for that, we have planned that that is one of the PhD graduate is working on this topic, that how we can monitor and the control process through applied machine learning, deep learning models, and that can control the process by looking to the surface. So here our idea is to quantify the process or classify the surface, and those classifications can be related to the subsurface defects, and that can give you the idea about the quality of the wells in a production environment. So yes, so it's like a monitoring and the control, because the monitoring is very much established, not only on friction stir welding, but a lot of additive manufacturing, but how to control. So the controlling needs a lot of efforts from the different research organizations and companies, and then we can have some solutions to control the process online, not offline. So that's it. I think I should stop now.
Yeah. Thank you, sir, for the wonderful talk. It was really enriching for us to hear you. Sir, can we take a few questions? There are certain questions in the chat box. Can I read them?
Yes, yes, please. Most welcome.
Yeah. Sir, the first question says, what advantages does FSW offer over traditional welding techniques in EV battery pack? Does it contribute to lightweighting of the structure?
Yes, just give me a second. I will stop sharing. Yeah. Is that okay now, screen?
Yes, sir. Yes, sir.
Yeah. Yeah. So for the question, for the first is a low distortion. That's a first answer. So distortion is quite less because the cooling plates are made of aluminum. And when you weld with the TIG, MIG, or let's say laser, then you have a lot of distortion. And the second answer that it saves a lot of money actually. So it's more sustainable than the rest of the welding process. Of course, capital investment is higher, but once the process is established, then uh, that's a more sustainable compared to the rest of the welding process. And the third answer is that's leak proof. So whatever the assembly you have in battery enclosures, the joint integrity is much better than the TIG, MIG, or laser welding process. So here you have better, I would say, the safety perspective.
Right, sir. Sir, the second question goes, whether FSW is more suitable over CMT for battery tray assembly.
Yes, and also I should not say it's a thumb rule, but it depends on what kind of joint configurations, right? But if your joint configuration allows support for backing bar, then I would say the friction stir welding is the first choice. And the reason why it is not easy to implement or easy to use, because there is no standard tool available. So one has to do design, a lot of design development, or they have to have the transfer of the technology so they can use the right tool and the parameters. And also in friction stir welding, apart from tool, I would add that the fixturing is also crucial. If you don't have the right fixturing, then you cannot have the better weld even. While in CMT, you can select the filler metals and standard wires or whatever is existing in the market. You can easily buy commercially, but in friction stir welding, it's not that easy to buy. So one has to establish, depends on the joint configuration, material, and the product.
Okay, sir. So the next question is, what kind of grain structures are obtained as compared to other methods?
The grain structure, I would say, is much more finer here because there is no solidification. And also, it's a severe plastic deformation. So the friction stability can define the structure from magnitude of second order, third order, fourth order, depends on the process. And that's why the allied technique called friction stir processing is used for grain refinement. So here you have significant grain refinement compared to the fusion methods for sure.
Okay, sir. So the next question is, what type of stresses are induced while friction stir welding is uh, occurring, and how to take care of this?
Yes, when you do any process, definitely you have residual stresses, but in friction stabilizing, the residual stresses are minimum, and those minimum residual stresses are coming through the thermal and mechanical deformation by the tool, as well as the clamping force. So yes, that's why this clamping was also important. That leads to distortion of the component sometime. So excess clamping force sometime is undesirable. But
Right, sir.
yes, there are some stresses, but it's less than the fusion routes.
Okay, sir. Sir, we can take few more questions, right? Because I believe the participants do have some more queries as well.
Yeah, no problem, sir. It's okay.
Yes, sir. Yeah. Uh, Sir, the other question is, how is FSW related to Industry 4.0? That is, can we make a digital twin for FSW?
Uh, yes, I think that's what I think all industries are working towards, whether it's so all equipment manufacturers, robotic and gantry system. So there are some features available now, but yes, it is possible, and I think the efforts are already there by KUKA robotic system and some of the gantry supplier.
Okay, sir. Sir, one very, I think it's a specific question. Sir, what will be the temperature difference measured in the thermocouple on the top of the tool, then the probe?
Yes, so there is, yes, of course, the you can have the exact temperature of the tool by measuring the temperature at the probe as well as at the shoulder. Because I would say the shoulder will be the one of the highest temperature because of the larger area. So, and also it depends on how long your tool, if you are talking about the back of the tool, how long, because you need uh, to measure the heat transfer along the length of the tool also, and also what kind of tool material. So normally the tool steel people use, right? So it all depends on what kind of tool steel and what is the thermal diffusivity of that material. But yes, at the probe and the shoulder, you can expect the highest temperature.
Right, sir. I think, sir, we'll take last two questions now. So the last but one question goes, when the welding speeds are high, like 2 meters per minute, the weld zone gets disintegrated due to less bonding time. So what can be your suggestion for mitigating this disintegration and to have a good microstructure?
Yeah, so it depends what joint the question is based on. So let me take in this way. It's a butt joint. Then I would suggest it's because of the force, downward force. So try to have more downward force. And if it is a lap joint, then I think it's mainly a probe design. So it depends what kind of joint and what kind of material. It's a cast material or sheet metals or extrusion. But it's mainly, I would say, the probe design and the small features on the probe, different threads and different flats and uh, so on. So either tool design or I would say downward force.
Okay, sir. And sir, I think this will be the last question. The uh, participant is asking, what is your opinion about 3D printing technology in friction welding?
Yes, it's a lot of things are happening in solid state additive manufacturing by using the same fundamental of friction stir welding, but it is in a low TRL, very initial stage. But for aluminum, yes, there is a lot of, I think, scalable things are happening, especially for building 2000 and 7000 aluminiums of large structure. So for aluminum, I think it's coming and it has a great future. But for hard alloys, there is a lot more to do with the tooling and other stuff. So far for aluminum, I think the technology is growing very fast when we talk about friction stir manufacturing.
Right, sir. So once again, thank you so much for this wonderful session. From the entire team, I extend my heartfelt thank you. Thank you, sir.
But thank you very much, and it was a pleasure to see you again, all of you.
Certainly, sir. Certainly a pleasure for us too. Thank you, sir.
Yeah.
Dr. Vivek, thank you very much.
Yes. Thank you, Badika sir.
Thank you. Thank you.
And yes, I wish you a happy Christmas tomorrow and nice holidays to everyone.
Likewise, sir. Thank you. Likewise. Yes, sir.
Thank you, sir. Thank you so much, sir.
Thank you, Manoj sir.
Thank
Thank
you.
you, sir.
Vivek sir.
Right, participants. So we do now move on to the second session for the day. Our next speaker has also joined. So join me in welcoming Dr. Antonello Esterita. He is an associate professor in manufacturing at the University of Naples, Federico II, Italy. Dr. Asterita is a leading authority in advanced manufacturing technologies, specializing in additive manufacturing, welding technologies, and material processing. He has played a pivotal role in supervising several PhD scholars on cutting edge research topics, including cold spray processes, hybrid manufacturing structures, and direct energy deposition techniques. He has more than 112 peer reviewed journal publications, 4 book chapters, and has been entrusted with leading numerous high impact research contracts with prominent institutions like CERN, Aviospa, and Italian Center for Aerospace Research. Sir is also involved actively in international collaboration, having served on scientific committees, chaired technical sessions, and organized renowned conferences such as SMT and AJP. He is also an esteemed editor and reviewer for various prestigious journals, including Journal of Material Engineering and Performances and Surface Engineering. His exceptional contributions to the field have earned him accolades like the ESA Form Scientific Prize and the ASM Silver Medal. Beyond academia, Sir is deeply committed to public outreach and has delivered numerous sessions to inspire the next generation of engineers and researchers. We are truly privileged to have him with us. Uh, Sir will be speaking on the topic of advanced manufacturing and sustainability, exploring innovative approaches that integrate cutting-edge manufacturing techniques with sustainable practices for a better future. So, with this brief introduction, I welcome you, sir. Uh, Over to you, sir.
So, dear professor, thank you very much for your very nice introduction. May you hear me?
Yes, sir. Very well,
Okay,
sir.
great, great. So, thanks you for your introduction, but more, thank you for inviting me, for giving me the chance to have a small talk to this event. It's very important for me. I'm very happy to have the chance to stay with you and to have the chance to deliver this talk. So once again, thanks for inviting me and thanks for your very kind introduction. Second point, so before to start my talk, I wish my best wishes of Merry Christmas to all of you. As you may know, in Italy, today is the Christmas Eve, so I want to extend to you the joy of this day and to your families. And then let's go to my talk. I will speak about sustainable advanced manufacturing. In the last year, sustainable manufacturing is becoming more and more important. We have a lot of issues in producing parts, in producing goods, but to make it in a more sustainable manner. So when we want to make more sustainable our production, which is the first thing that we have to do? The first thing that we have to do is to measure the sustainability. Okay. Sustainability, according to the international standards, relies on three main pillars. The first one is the economy. The second one is the environment. The third one is the society. Okay. As industrial engineer, usually we don't think about the social sustainability. The point that is more common to us, let me say, is the environment sustainability or the economic sustainability. Concerning economic sustainability, I don't want to speak more about this point because it's more, let me say, a kind of stuff for people working in economics and in administration. So let's stay focused on environmental sustainability. So when carrying out our production processes, we should try to reduce the consumption of energy, the consumption of raw materials. We should try to reuse materials as more as we can. So when designing new products or new processing paths, we should think about the environmental impact. How to measure the environmental impact of goods and production systems? Well, we have an international standards, the ISO international standard for life cycle assessment. So we can perform life cycle assessment of our product to measure the impacts that are related to our products in all the life cycle of the product, starting from the extraction of the raw material, the production path, and then the use and the end of life management of a product. Again, to perform the life cycle assessment, it requires a lot of data. So when carrying out our processes, we should introduce a sensor to measure the energy consumed, to measure the gases that we are using, to measure the use of lubricant. So when we speak about sustainable advanced manufacturing, we are speaking about manufacturing processes which are sustainable. So when we say sustainable, we are saying that we are reducing the footprint of these processes on the environment by reducing the consumption of energy, by reducing the consumption of raw materials, by reducing the consumption of lubricants, and so on. Okay, this is the starting point of sustainable manufacturing. There are also some other people that are working about green manufacturing. Green manufacturing is a kind of manufacturing in which you reduce environmental impact, but you don't care about the economic issues. As we know, when you manufacture something, you manufacturing this good to sell it and to make a profit over the selling of this product. So we have to go towards sustainable manufacturing. After this brief introduction, I would like to present you some applications that we are developing in our labs. The first topic that I would like to speak on is the sustainability of additive manufacturing. So you already had a very interesting session on additive manufacturing, so you will speak a lot on additive manufacturing, but one of the points is how to reduce, how to measure the energy consumption and environmental impact in 3D printing. Again, when you produce something through laser bed powder fusion techniques, for instance, selective laser melting, or it's the same electron beam melting, the final surface roughness of the part sometimes is not adequate for high performance. Yes? May you hear me?
Yes, sir, you're audible well.
Okay.
Yes, sir.
Okay. Because I just heard something saying something, so I
Yeah,
feared.
it was probably some disturbance from some of the, yeah.
Okay.
Sir, sorry, once we are talking, sir, do you plan to share some slides?
Yes. Now I'm going to share some slides.
Okay, sir. No problem, sir.
Okay, I just did a brief introduction to get inside the topic, and
Correct,
then
sir.
I will show the slides.
Sure,
Okay, so when you work on additive manufacturing and when you produce high performance parts, for instance, for rockets engine or so on, you must reduce the surface roughness of the part because usually after additive manufacturing, the surface roughness that you obtain is not good enough. for this high performances application. So you need to do a machining step, or let me say a surface treatment step after the 3D printing. When considering the energy consumption related to an additively manufactured part for high performances application, you need to consider both the step, the 3D printing part and then the machining part. So what we will see in a bit, I'm going to share a presentation, an application that we are carrying out in collaboration with an Italian company working in manufacturing of parts for rockets engine, to study the energy consumption related at both the 3D printing part and the final machining, to have the energy consumption related to the product. Because again, when we speak about sustainable manufacturing, we have to take care to all the different steps that are required to produce a finished part. So if we do additive manufacturing, sometime, let me say always, for high performance application, for aeronautic and space application, we need to do a surface treatments, that it could be machining, it could be a chemical treatment to reduce the surface roughness. So we have to consider both the processes. Okay, let me share my screen. Okay, I guess that you can see my screen. This is a work that we did in collaboration with an Italian company. What we did, we starting from Inconel 718 powders. You may know this is the alloy that is most used for space application, and we used a concept laser machine and then a machining center at CNC turning machine. Okay. And we measured the energy consumption of all the different stages of the process. We varied the process parameters to find out which is the correlation between the process parameters and the energy consumption, because this is another point. Over measuring the energy consumption in 3D printing and machining operation, another most important thing is to reduce this energy consumption. How to reduce this energy consumption? You can find out that by varying accordingly the process parameters, you can achieve some condition in which the energy consumption is lower. So another point that we are going to study is to change the process's condition, trying to achieve the condition in which the energy consumption is the lower possible. So we started from those powders. We manufactured some samples, the cylinders. Why cylinders? To have a very simple geometry to use as reference to measure the specific energy consumption. So we printed a lot of samples by varying the laser power, the scanning speed, and the edge spacing. So we did 27 different combinations of processing parameters, and we calculated, let me see, theoretical energy density for each condition. This is a very common formula used in 3D printing, so you can calculate the theoretical energy density. Why I'm speaking about theoretical energy density? Because this is the energy provided by the laser beam, but then the energy that is effectively drained by the base material, by the powder bed, it is depending on the packing factor, it is depending on the density of the material, it is depending of the particular properties of the material that you are considering. So this is very important. This is the theoretical energy. So this is the energy that we are giving to the material. But the effective amount of energy that the material is draining from the laser beam is also depending on the shape of the powders, the packing factors, and the physical properties of the material itself. So another important point in trying to reduce the energy consumption is to increase the percentage of energy which is effectively drained by the powder bed material. Okay, so another important point is to choose the shape of the powder, is to choose the properties of the powders to increase the amount of energy which is effectively drained from the laser beam. Okay. So we did this 27 combination, and after the processes, after the 3D printing process, we did machining on all of those samples to couple the energy consumed during machining and the energy consumed during the 3D printing. Okay. So how to measure the specific energy consumed for additive manufacturing? So in the first important point is to measure the energy. So we use this device. This is just a power analyzer that we put between the machine and the socket in the wall, you have to be very, very careful in designing this kind of equipment, and also in designing the intermediate stuff that you put inside to be able to measure the energy required from the machine. This is a three-phase equipment, sorry, with the 3 lines and the neutral lines. Okay. And this equipment allows you to measure the energy required during the process. Once you measure the energy, sorry for cough, you will be able to calculate the specific energy consumption for additive manufacturing. So you can write down in a first instance that this specific energy consumption is the ratio between the energy required for the whole build versus the mass of the samples you printed. But you can also write that the energy required to obtain the build can be calculated as the energy required by the laser plus the energy required by the auxiliary systems, because you have, let me say, a circulating gas pump, you can have a vacuum pump for other equipments, you can have other auxiliary machines, so you can divide the energy that you spent for the whole build into amounts: the energy required by the laser, which is related to the process parameters, and the energy required by the auxiliary systems that sometimes is not related to the process parameter, is only related to the time, to the processing time. So another good point is trying to reduce the processing time, because by reducing the processing time, you both increase the productivity of your system and you both decrease this amount of energy. Okay. Again, you can calculate these two amounts, like the power required by the laser plus the power required by the auxiliary system, both of them multiplied for the scanning time, so for the production time. But how to write down the scanning time? The scanning time can be seen as the ratio between the volume of your build and between the velocity, that can be write as the number of layers multiplied for the time required to print each layer, for the hatch space, for the scan velocity. Okay. At the end, you can obtain this formula that gives you an idea of the specific energy consumption in additive manufacturing. You have the power required by the laser plus the power required by the auxiliary system versus the number of layers, the density of the powders, the thickness of each layer, the hatch space, and the V-scan. So with this formula, you can easily calculate the specific energy consumption. And again, when you choose the processing parameters, you have to be aware that you are moving inside this formula. So by accordingly choose the process parameters, you can try to reduce the specific energy consumption. Again, this is a theoretical energy consumption, because we should also consider the amount of energy that is effectively drained by the material. In machining, the specific energy consumption of machining is quite simple to be calculated. It is the energy required by the machining versus the mass of machined material, the mass of removal material. So if you want to calculate the specific energy consumption total, so related to the product, you have to have the specific energy consumption of additive manufacturing plus the specific energy consumption of machining by coupling those two formulas. Okay. This is what we did in our paper. Okay. In our activity, we measured both the quantities. So in this formula, we don't have the, let me say, theoretical calculation, but we have the actual calculation, because we performed experiments and we measured the energy consumption. For instance, you can see during the production period, you have the period in which the laser is working, you have a very high power consumption, but then you have the period in which the laser is shut down, in which the power consumption drops. You know, you have the first layer, then the laser operates, then you have the second layer, then the laser operates, and so on. So during the processes, you have some time in which the laser is operating and some other time in which the laser is not operating. Okay. Then we performed the machining operation to achieve a very good surface finishing. Let me say, to achieve the surface finishing required for space application, and we were able to calculate the specific energy consumption total. Again, one question should be, why did we use a lathe machine and not a CNC machine? Well, because in this activity, we want to focus our attention on the contact between the tool and the cutting tool and the sample. If you have a CNC machine, you have a lot of auxiliary systems. So in studying the energy required for the actual working process, for the actual cutting process, you have also to calculate, to consider the influence of those auxiliary systems. So aiming to try to focus the attention on the interaction between the cutting tool and the material, we decided to use this lathe machine that has a very low number of auxiliary systems. At the end, we found a direct link between the specific energy consumption in additive manufacturing and the energy density. As you can see, this is unexpected results. By increasing the energy density, you increase the specific yes? Everything okay?
Yes, sir. All good, sir.
Okay. So as you can see, by increasing the energy density, you also increase the specific energy consumption. We have a kind of, let me say, linear fit between these two entities. So the first immediate results is that you should try to reduce energy density in 3D printing to reduce the energy consumption. Another interesting link is the link between the density of the printed parts and the energy density adopted, because in additive manufacturing, to achieve the maximum density of the parts, your main aim, it will be, of course, to achieve a relative density of 1, but it's very difficult. Here we have, as you can see, 0.99, so we achieved extremely high density of the final parts, but you can see also that there is a correlation between the density of the part and the specific energy consumption. Okay. So again, another point in sustainable advanced manufacturing is to link the performance that you are seeking, in this case, the density of the printed parts, with the amount of energy and the impact that you are generating to produce those parts. So again, something that you have to consider. Okay. We also tried to correlate the specific energy consumption with the different processing conditions that we varied to evaluate if our formula is good enough to catch the development of the process. And we can say that the formula that is proposed here is good in predict the experimental results. So as you can see, by increasing the H distance, you reduce the specific energy consumption. By increasing the velocity, you also reduce the specific energy consumption. And by increasing the power of the laser, you increase the specific energy consumption. Okay. Each of these diagrams is produced by fixing one factor and varying the others. So you can see that the formula that is portrayed here is good in catching the experimental development of the process. So you can use this formula to adjust the choice of the process parameter to choose the processing conditions that are the best relating to the specific energy consumption of additive manufacturing processes. Then we also measured the surface roughness to correlate the specific energy consumption to the roughness, because in the previous slides, this one, we correlated the specific energy consumption to the density of the 3D printed parts. But as I said, when you perform post-building treatment, you also want to reduce as more as possible the surface roughness of the parts. Okay, so you need also to measure the roughness before and after the machining process. We used a three-dimensional scanner to have the 3D representation of the surface and to calculate, according to the standard, the surface parameters for roughness, because usually what you do is to calculate the linear parameters for roughness, but in 3D printing, the linear parameters are not detailed enough to catch the actual shape, the actual geometry of your surface. So the parameters that are more useful to capture the surface are the surface parameters. Again, we use a Leica DCM 3D confocal scanner to acquire the surfaces and to calculate the surface roughness according to this standard. The results that we obtained were various. We can see that there is no clear relation between the 3D printing process parameters and the roughness parameters, but this is not a big problem because we are going to do machining. We performed machining operation and we found out that the most of the energy is the one consumed for additive manufacturing. As you can see, when you see the specific maybe there is someone with the open microphone. Okay, fixed. So as you can see, when you calculate the specific energy consumption total, you have that the most of the energy is consumed by the additive manufacturing. Okay, in machining operation, but here, because we are only considering the surface finishing, so we are removing a very small part of material, so the energy consumption is limited with respect to the energy consumption of 3D printing. But it's because it's just, you know, a kind of finishing process. Another important point that I want to share with you, we are going to change the presentation, is that you have differences between the environmental impact of additive manufacturing and the environmental impact of machining. Why? Because in machining, you have a waste of material because you are producing scraps and so on. Okay. Okay, I will try to manage it. Thanks for the suggestion. So the point is that in additive manufacturing, you spend much more energy, but the use of material is more efficient. In machining, the energy required is lower, but you are wasting material by producing scraps and so on. So in this particular case, in which we are performing just a surface finishing to reduce the surface roughness of 3D printed parts, as you can see, the most of the impact is related to the 3D printing process. But if you want to focus on a machined part, you will be see that the most of the impact is related to the machining process. And again, in machining operation, it's very important the use of lubricant. Why? Because in the past, also nowadays, in most of industrial application, you have a very high use of lubricant, okay? And the lubricant is responsible for the most of the environmental impacts. We have to try to reduce the use of lubricant. You will see in a next presentation that I'm going to show you how the use of lubricant will affect the sustainability of the process. Okay. Just give me 1 second to share my screen. Okay. This is a study that we carried out in collaboration with the Ohio State University. Let me again share the screen. How to present? Okay. This is a work that we carried out in collaboration with the Ohio State University, trying to reduce. This is a work that has been made by a PhD student of mine, Ersilia Cozzolino, and Ammetti, okay. And in this work, we tried to study the energy consumption related to the use of ring laser. So we, in 3D printing of Inconel, we varied the energy distribution, trying to find out if it's possible, by varying the energy distribution, to find out process condition in which the energy required is lower. Again, if you want to reduce the energy consumption, you have to change the processing condition. And we did this experimentation on the same Inconel materials that I previously presented, but by using a selective laser melting machine, but by varying the profile of the laser beam from a Gaussian profile, which is the most used one, is the one that we use in the previous experimentation that I shown to you, moving to a ring laser. In ring laser, the shape of the laser is different, and we tried to understand if by varying this profile, we can reduce the energy consumption. Okay. Again, we performed a full experimental campaign and we measured the power consumption over time. You can see the power consumption over time for both the processes, Gaussian laser and ring laser. By using ring laser, we were able to improve the productivity and to reduce both energy consumption and build time. As you can see, each time that you reduce the build time, you increase the productivity and you decrease the energy consumption. Why? Because if you remember the previous formula, the formula for specific energy consumption in additive manufacturing, you can see that by reducing the time, the process time, you reduce the energy consumed. Why? Because you are reducing the operating time of the laser, but what is more, you are also reducing the operating time of auxiliary system. And for a 3D printing facility, the auxiliary system are more important. Again, in real industrial application, when you consider the auxiliary machine, you should also consider the air conditioning of the room in which the operation are carried out. We are conducting a study with an Italian company, and we are trying to measure the energy required to keep the printing condition in the room which is effectively used for printing operation. And we can see that by reducing the processing time, will lead to a dramatic reduction of the energy consumption, because you also save the energy required to keep on, for instance, the air conditioning in the room in which the printer is operated. Okay. We did a more detailed study for electron beam melting. This is a study carried out in collaboration with CIRA, the Italian Center for Aerospace Research. Why we are doing all those different experiments with the different printers, with the different partners, trying to validate in the more general manner possible our formula. Okay, so the formula that I presented, we are trying to use that formula with data, experimental data coming from different processes, different printers, trying to have a clear correlation between the data for different manufacturing environment. In this work, we studied titanium 6 aluminum formvanadium, which is an alloy mostly used for space and aerospace application, and we used an electron beam melting machine. As you may know, the main difference between selective laser melting and electron beam melting is that in selective laser melting, the power source is a laser. In electron beam melting, the power source is an electron beam. In electron beam melting, you can have an higher layer thickness, higher productivity, but you need to keep the building chamber under vacuum condition, and usually the vacuum is much more expensive than the gas, of course, and you need to keep the whole printer job at a preheating temperature for titanium of more than 700 degrees. This is also very important because in calculating the sustainability of the process, you will see that this preheating temperature has a not negligible effect. In this pie chart, you can see the use of energy for the different stage of the process. You can see that the most of the energy, of course, is required for the printing, but you have a non-negligible part of energy that is due to the preheating of the whole job, and another non-negligible part that is related to inertization. Okay. So this is let me say, the flow chart of the process, and we measured the amount of energy required for each step. Again, we did machining operation after the 3D printing. You can see here, this is the sample printed through ABM. We did the machining operation by using a conventional lathe, again, trying to reduce the use of auxiliary systems in machining, and we obtained a kind of equation to calculate the power actually required to perform machining operation, because our aim, as I previously said, is to produce a formula that you can use to predict the energy required to perform both 3D printing and machining processes to obtain final parts. Okay. Again, we performed machining operation under different conditions. You can see that the spindle speed varied from 440 revolution per minute to 1200 revolution per minute. We also varied the depth of cut, and we used Sandvik Coromant tools with an industrial lubricant. So we used state-of-the-art tools with the lubricant most used in industrial environment, at least in Italy. And we carried out a full experimental campaign by varying the cutting process parameters, trying to develop this formula, trying to develop this equation that allows you to calculate the total energy required to perform a machining operation. Again, we're trying to see if the machining data can be related. Here, this is very interesting, is material removal rate, is how much material you remove in a given amount of time. Again, this material removal rate that it can be seen, if you remember one of the previous slides on additive manufacturing, it can be seen like the printing time. You can have a kind of linear relation between the power cut required and material removal rate. Okay. Again, we measured the roughness, because another point that you have to in sustainable manufacturing is to make sure that your product, meets the requirements for the application in which this is put. So you have to correlate the final performances, in that case, the roughness, with the total energy required. We can see that we can obtain very good results in terms of roughness with a very low energy consumption. But to do this, of course, you have to make sure that you are doing your operation under the best processing condition possible. We also had a look to the milled surfaces. Of course, and at the end, this is a very important result. So we were able to produce a kind of map that relates the material removal rate, the total energy consumption, and the roughness that you achieve. So you can move in this map by highlighting the condition in which you achieve the material removal rate that you want, the roughness that is the target of your process, because for a given application, usually have a roughness limit that you have to respect, and the energy total required to perform the process. Okay, so at the end of our experimentation with our equation and with the experimental data that we achieved, that we used to put inside the equation that I showed you, you can have those maps in which you can correlate the energy total required, the material removal rate, and the roughness that you achieve. Okay, this is very useful for industrial application in the aim to achieve sustainable manufacturing, because by respecting the roughness limits that you have for your given application, you can choose the energy total and the material removal rate that allows you to achieve this point. Okay. And let me change. We are now going to see another important application that we also are carrying out. Sorry for the laptop. It's not. This is not. Okay, yes. Okay, another interesting application that we are carrying out is the correlation between the lubricant use and the life cycle impact assessment of the part. Which is the correlation between the use of lubricant and the life cycle impact assessment of the part? The problem in using lubricant is the point that you have to dispose the lubricant after the process. The disposing of the lubricant is much more impacting than the production of the lubricant itself. So you have to manage between two different phenomena, the tool wear and the use of lubricant. Because let's focus our attention on machining. let's focus our attention on machining of titanium, as we did in the industrial case that I just shown to you. Okay, admit that there is still a lot of people that is asking for admission. I usually admit them. Okay, as I just said, in machining you have two different aspects. You can either use lubricant or you can do not use lubricant. Which is the problem? Let's consider the use of lubricant. The use of lubricant allows to you to reduce the tool wear and to reduce the temperature achieved during the process. But then you have to dispose the lubricant. If you don't use lubricant, from one end, you have an increasing tool wear. So you have to change the tools with a higher rate. But from another point of view, you don't have the lubricant, of course. So you don't have to take care of the disposal of the lubricant. And what is also more important, you can achieve an increasing of the temperature during the cutting process. But by increasing the temperatures during the cutting process, you are going to reduce the properties of the material, because as you may know, for metallic material, higher is the temperature, lower are the mechanical properties. So for some application, for instance, for very difficult to cut materials, you can do machining operation without lubricant just to increase the temperature to reduce the cutting specific pressure that should be achieved during the cutting operation. But which is the more sustainable approach? Because again, if you use lubricant, you have lower consumption of tools, so lower wear of tools. You can have higher cutting speed, so lower cutting times. But then you have the lubricant. As some studies says that the use of lubricant is responsible for the 20% of both the cost and the environmental impacts related to machining operation. On the other hand, if you don't use lubricant, you are going to if you don't use lubricant, you are going to increase the wear of the tools, so to increase the number of tools required to perform a given machining operation. So which is the best solution? It's up to you. It's up to your particular case. It's up to your very particular application. So you have to calculate the impact under the two conditions. How to calculate the impact? By performing a life cycle assessment analysis. The life cycle assessment analysis is an analysis that is ruled by ISO standards that allows you to calculate the environmental impact related to the fabrication of one product. But why sustainable yes? Okay, but why sustainable manufacturing? Which is the reason behind the introduction of sustainable manufacturing? Let me show you some data. Okay. Okay. Again, let me share the screen. Okay. So, as you can see here, we have the Sustainable Development Goals as set by the organization by the ONU, the United Nations Organization. So as you can see here, to achieve a sustainable development, we have some goals. As industrial people, we have to focus our attention on industry, innovation, infrastructures, sustainable city and communities, and decent work and economic growth. So our goal as manufacturing engineers must be to reduce the impact of manufacturing operation by introducing new application, as I shown to you the ring laser, for instance, in additive manufacturing, as developing new equation, as I showed you the equation we are developing to calculate the energy required to both machining and 3D printing operation, trying to minimize the impact, the environmental impact of the manufacturing of goods. Okay. Here we can see this data coming from the Japanese Ministry of Economy, but it's a kind of mondial study. We can see the energy consumption by sector. So we can see that the most of the energy consumed is consumed by manufacturing. So as people working on manufacturing, we have to focus our attention on the fact that the most of the energy which is consumed by manufacturing. But again, we also have energy directly consumed by manufacturing, but let me say, also energy that is indirectly consumed by manufacturing. Because if you have a look to this transportation amount, we can assume that a part of this transportation is used to transport goods which are manufactured. So the energy consumed for manufacturing is even higher. So again, we can see the more or less the same results, but made for China. So aiming to compare the footprint of different countries. And again, we can see that the most of the energy is consumed for manufacturing operation. So as I shown you in the previous part of this very short talk, as you can see, a very important point in manufacturing operation is the energy consumption, because the most of the energy that the world consumes is consumed by manufacturing. So as manufacturing engineers, we have the responsibility to study the energy consumption related to 3D printing, to machining, to all the manufacturing operation that we carry out. Okay. Again, as you can see, also the most of the CO2 emissions are related to manufacturing. As you can see by those diagram, you have that the most of the CO2 emissions are embodied in manufacturing products. What does it mean? What does it mean, CO2 embodied emission? We have to be familiar with the concept of embodied energy. Each manufacturing goods or each good that we have, each product that we have, has an amount of embodied energy. Which is this embodied energy? Is the amount of energy that has been spent to produce this part, to produce this good. So we can say that at the end of the production path, we have an amount of energy that has been spent to produce this part. This amount of energy is called embodied energy. Again, we have some emission that are related to the manufacturing of this good. So a particular product, a particular good has a kind of embodied CO2 emission. And as we can see, the most of the embodied CO2 emission are related to the manufacturing steps. The most of the embodied energy is related to the manufacturing step. This is the reason why we focused our attention, as I shown you in the previous part of this talk, on measuring the energy consumption, on providing equation to predict the energy consumption, because the energy consumption and the embodied energy of a particular product immediately gives you a kind of index of sustainability of this part. The lower is the embodied energy, the lower is the embodied CO2 emission, the higher is the sustainability of the part that you are producing. Let's go back to the presentation. Okay. And as you can see here, in a first, sorry, but I can, yeah, okay. As you can see here, in a first period, the carbon emissions were continuously increasing. From the first decade of this century, we are decreasing of the CO2 emission. Why? Because we are trying to focus our attention on a more sustainable manufacturing. So by focusing our attention on a more sustainable manufacturing, we are also able to reduce this kind of impact. Again, another very important resource is the water. As you can see, the most of the water is consumed, yes, for farming, of course, but then we have a lot of water that is consumed for manufacturing operation. In manufacturing operation, we have again to focus our attention in the consumption of water. The water is a very precious resource. This is the diagram of water consumption in Europe, and as you can see, this water consumption, the most of the water consumption is related to manufacturing operation. Okay. As I told you, the use of lubricant in machining. the most of the industrial lubricants are made by water and then by some polymers or some oils that are addicted to the water. When you use lubricant in machining, you are increasing the water consumption of machining operation. Okay. This is something that we have to focus on. So when studying machining operation, you have to study both the consumption of energy and both the consumption of water. Okay, so also water is a very precious resource that is used for manufacturing operation. Okay, again, the emission of CO2. As you can see, a lot of emission are produced by manufacturing. But have a look. We have the first emission producer is manufacturing, but then we have electricity, gas, steam, and air conditioning supply. But the most of this electricity, gas, and steam are supplied to manufacturing. So again, the manufacturing is the most consuming resource sector of our society. We consume more energy and we produce more greenhouse gas emission in manufacturing rather than in agriculture, rather than in households. So we should be very careful in performing machining operation, performing manufacturing operation. So the equation, the systems that I already presented to you should be considered in big details, trying to reduce the impact of those operations. Okay. As you can see, again, focusing on the European Union, where the CO2 comes from, it came from manufacturing and energy. But again, the most of this energy is used in manufacturing. So again, the most of the CO2 emissions come from manufacturing. So as manufacturing engineers, we have to focus our attention in reducing the energy used for manufacturing operation, as I've shown you. Okay. Another very important point is the resource productivity, is another concept that I would like to introduce to you, is the productivity related to each kilogram of material. So this index tells to you how is your production is efficient, how are you efficient in reducing the scraps, how are you efficient in reducing the unwanted parts, how are you efficient in reducing the defects. Again, let me. Sorry for stopping. Yes, sorry for stopping the sharing of presentation, but I really like, let me say, a more direct interaction. So there are some parts that I really like to discuss. So. Okay, fixed. So. That's the last slides introduced you the concept of resource productivity is the index of productivity related to the use of any resource. So how good we are in using materials. So out of 1 kilogram of steel, which is the money that we produce, how good we are in taking value from the material, how good we are in using and using again the same material. How circular is our economy? For circular economy, we intend this paradigm in which we have the material entering into the system. For instance, I'm manufacturing a steel can for Coca-Cola. Then after drinking Coca-Cola, I recycle the steel can to obtain another product in a kind of circular paradigm. So the resource efficiency metric, which is a metric proposed by the World Forum for Health and for Manufacturing, is a metric in which I measure how good I am in using material, so which is the productivity linked to the use of 1 kilo of material. Okay. Higher is index, lower is the environmental impact of my production system, because higher is the index, higher is the use that I do of material, lower are the scraps. In this view, it's very important to reduce scraps, of course, but also to reduce defects, because let's imagine, do you remember the concept of embodied energy? If I manufacture a part, but at the end of the manufacturing process, this part has a defect, so I cannot use this part, all the embodied energy, all the embodied emission are waste, completely waste. So a very important point in sustainable manufacturing is to reduce the energy consumption, to reduce the use of material, to reduce the occurrence of defects. Because when a defect occurs, you are reducing the efficiency of use of the material. So you have to take care to have a lean production to reduce defects. So all the system to control the process, to manage the operation should be implemented to reduce the occurrence of defects. Okay. So you have to go through the direction of zero-free product or defect, sorry, near defect-free production or near zero defect production. Why? Because the defect is not only an economic cost because you are going to not using a part that has been manufacturing, but is a waste of resources. Let me show again. Okay, so this index, the resource productivity, is very important. Okay, is very useful. The same index can be calculated for energy. Those diagrams are quite old. It's very difficult to find out recent trends for energy because to perform this calculation, you have to rely to well-consolidated data, and sometimes you need a kind of backlog to analyze and acquire this data. But as you can see, you can calculate the same index for energy productivity. Okay. So again, how good are you in using the energy? Which is the productivity related to the energy that you use, and is expressed in euro of, so in money of product produced on the kilograms of oil equivalent. So the oil equivalent to produce the amount of energy that you have used. Okay, this is also a very important index and tells you how good you are in using energy. Okay. All those index can be merged in this very important index, which is the Eco Innovation Index. Again, this index says how good are you in introducing innovation in manufacturing to reduce the impact, to enhance, let me say, the energy productivity and the resource productivity. Okay. But again, from an industrial point of view, if you increase this index, what are you increasing? You are increasing the profit for your company. So this kind of metrics, resource productivity and energy productivity, are of course good for green manufacturing and are good for the environment, but also on the other hand are good for the profit of your company, because by increasing those index, you either reduce the environmental impact but increase the profit for your company. Okay. Don't worry, I will share with you those slides, so you will have here all the definition of these parameters. Okay. So as manufacturing engineers, we have to pay attention to the material choice, trying to choose material with a reduced environmental impact. We have to study the resource used in manufacturing path. We have to study the life cycle of our product. Then we have to introduce innovation in manufacturing process and operation, trying to reduce the energy consumption. And this part, of course, is out of our competence. This is the government, the companies that release laws and regulation that, of course, we have to follow. This is the last image that I will show to you. This is the Aral Sea. Is in Russia, the previous Soviet Union. You can see the Aral Sea in 1973, and you can see the Aral Sea today. So because in that region, they had a very, very strong steel-making industry. They didn't follow any environmental regulation. So the final results was to have a lake or a sea in 73 and a kind of, sorry. So sea, this is the Aral Sea in 1973, and to have a kind of desert today. So this is what happens to the environment when you carry out industrial operation not taking care of the environment. But of course, when your environment changes from here to here, it's not only bad for the human health, but it's also bad for the profit, because you don't have the water, you have to find water from another point. So this becomes a problem. Okay, so okay, again me. So again, this is the final part of this grandma. Yes, of course, green synth yes, green manufacturing can be achieved through additive manufacturing, but you have to focus your attention in producing an additive manufacturing process which is conscious, which is based on a responsible consumption of energy and materials. So this is the last message of my intervention, is to focus on green manufacturing, is to think about the sustainability of the process, to think about of the energy consumption. And in this direction, we are developing the equation that I shown to you. We are also doing a lot of experiments to populate this equation, trying to predict the energy consumption related to manufacturing processes. So in that way, when you are at the starting part of the production process, when you have to choose the process parameters, you can choose the process parameters that on one hand ensure the performances of the product that you want. On the other hand, will reduce the energy consumption, reduce the use of material, and increase the efficiency in productivity. And by reducing the environmental impact, as I shown you, you will also increase the profit for your company, which is good, because you are doing at the same time a reduction of environmental footprint by reducing the use of energy and reducing the use of the material, but also you are increasing the profit by increasing the productivity by reducing the costs. Okay, I think that we have time for question now, because I managed to divide my time in a, let me say, presentation time and question and answer time. So I hope that you enjoyed the presentation, and I hope that there are many questions to discuss the topic. Again,
Certainly,
thanks.
sir. Thank you, sir. Certainly, it was a very informative session, and we could relate to the impact of manufacturing in our carbon footprint, and not just the carbon footprint, but even in the other sectors pertaining to water security as well.
Yeah.
So the participants certainly are requested to type in their questions. I believe, sir, you already answered the first question. So the second
Yeah.
question goes something like, can we say that lithium manufacturing is
Yeah,
actually
yes, for
impacting the
sure. I am ready.
perceived
Yes, this is a very big problem. The electric vehicles are a big topic of discussion in Europe, because from one hand, you are forced by the government to buy electric vehicle, but from another hand, you perceive that the lithium manufacturing is very bad for the environment. So we are discussing about the spreading of these electric vehicles. So this is exactly the point, because when you speak about life cycle assessment, you have to consider the full life cycle. So when you consider the full life cycle of an electric vehicle, the production of lithium is a very important concept. So you have to perform those life cycle assessment by coupling on one hand the benefits related to the electric vehicle, but on the other hand the issues related to the battery and lithium manufacturing. So those are two topics that are in competition, and this is the importance of tools like life cycle assessment, because you can compare from one hand the benefits of electric vehicles, from another hand the drawbacks of lithium and battery production, and of lithium and battery dismission after the use of the electric vehicle. So coming to your question, yes, I agree with you. We say that we can say that lithium manufacturing is actually impacting the perceived sustainable benefit of electric vehicles, because that is a topic of discussion, is a topic on the floor, the manufacturing of lithium-based battery. Okay, yeah. Then we have another question. Is there any interaction between the process parameters of additive manufacturing? Which parameter is most significant in waste reduction? Okay, we have to consider that waste reduction is a big problem in additive manufacturing, because you have, of course, the powder that are inside the job. Some of those powders will be part of the final product. Some other powders will be not part of the final product. So those parts maybe can be referred as waste material, but the point is not to use those powder as waste material, is to try to recycle those powders, trying to develop a post-building treatment to have particles that can be used again and again. Even there is for instance, the European Space Agency, the ESA, there is also an ESA standard to reuse the powders after 3D printing, because the most affecting factor is how good are you in recycling the powders. So the most impacting parameter is the recycling of the powders, and also the laser power. Sorry. So during the process, you should try to reduce the laser power as more as possible, trying to reduce the effect of the process on the particles that will be not part of the final part. And after the process, you must try to increase the recycle of the powders, trying to reduce the waste. Is it feasible for developing countries? Yeah, this is a very, very big questions. So how make it affordable? I don't have an answer to these very good and very important questions, but I think that all the companies and all the governments should work together to make these technologies cheaper and cheaper, to make it affordable for developing countries. So I think that this is something that all the world should consider. So trying to reduce the costs of some techniques to make it affordable for all the countries. Allora, something. Yes, this. Okay, let me read the question. May all of you read the questions?
Yes, sir. Can I read the question?
Oh, yes. The
Yeah.
last one, because it's very interesting. All the questions are very interesting, but this last one is very interesting with a lot of points. So
Yes,
please.
sir. Yeah, so the participant tells us 3D printing technology, product manufacturing time and material usage is less. Is it so? And latest machine developments. So, okay. Some of the latest 3D printing machine boast impressive energy efficient features like multi-laser printers. The other is an open system architectures. So, sir, what is your view on them? So, multi-laser
Okay.
printer or a
Okay.
open system architecture? Do they
Okay.
really make things energy efficient?
Okay, we use an open system because in the slide that I shown to you related on ring laser, in that case, we are using an open architecture in which we can change the laser using ring laser. Of course, the newest additive manufacturing facilities allows you to reduce the times, allows you to reduce the energy consumption. So you effectively have processes that are very, very effective. But on the other hand, it's not enough. So you have to work more and more to reduce also the costs of those machines, because those new machines with the multi-lasers and open system architecture are very, very expensive. Yeah, this is the point, which is the cost of your equipment. If we just consider the cost of the equipment, I would say like 1 million euro. But we are not considering the cost of, let me say, of the research that I am not computing. So let me say 1 million euro to buy the different parts. But then there is our work, the work of the PhD student to integrate all the parts together. I have no idea which could be the industrial price, but something more than 1 million of euro. And also in the last November in Europe, we had the Formnext, which is how to reduce it. You will reduce this cost when the research goes on, so the production increase. So by increasing the number of equipments available, you of course reduce the cost. It's the same of cars. You know, at the beginning of the last century, you have only very few cars for very, very, very rich people. But now the cost of the cars is going down because a lot of people has the car. So this is the point, to spread these manufacturing processes, to open those processes to new application, so you can reduce the cost. It's possible to. Which is the probe cost? Which cost are you referring to? What do you mean by probe?
I think he's referring to the laser scanner, I believe.
Okay. The laser suit. Uh, I don't know, because I am not a laser expert. We just buy lasers and use for our manufacturing operation. I hope so. I hope so that they will reduce the cost. But I have no idea about which is the actual cost of a laser source. How is the mechanism of producing the costs? of formation of the cost for those applications. But I hope so, because now lasers are very, very expensive. Also very expensive for multi-laser machine, as you mentioned, is the control, because you have to control different lasers working on the same area. You have to control the overlapping. So those controls are very, very expensive. But I don't know how to reduce those costs. But it will be a good point for people working on both additive manufacturing and laser processing.
Right, sir. Sir, if you can just add one more detail. So I think we touched a lot on the sustainability aspect, the energy related aspect. Sir, can you share something on the toxicity or pollution related aspect as well? Because
Yes.
sometimes these are also becoming an environmental concern, apart from, of course, the energy facet.
Okay, yes. When we speak about additive manufacturing, you have the problem of emission, but you know which is the most impacted additive manufacturing sector by... Okay, can you share your email ID? I will write... I cannot write my email ID. There is one attendee asking my mail address. I'm trying to write, but... Okay. This is my university mail ID. And this is my private mail ID, are more or less the same. The first one is at University of Naples. The second one is at gmail.com. Okay. So coming back from the toxicity and emission, concerning 3D printing, one sector is the 3D printing of polymers. In 3D printing of polymers, you have a big problem of emissions, a big problem of toxicity. So, which is the point? You have to perform those operations in controlled environment. If you remember when I spoke about the auxiliary systems energy consumption, one of the auxiliary systems is the system in the room to remove and to treat the emissions. But which is the problem with the polymers 3D printers? Is that right now the 3D printers for polymers are very cheap. So you can buy on Amazon for $200 or $150, depending on taxes, a 3D printer equipment you put, for instance, in your room. I have students of mine that in their room, at their home, they have very small 3D printers and they print plastics. The mechanism of fused plastic deposition is that you heat up the plastic and you produce the final part very, very cheap. The point is the toxicity of the emissions is a point that there is not so much research, but it's a very interesting point, because if you perform those operations in industrial environments, you have to take care of this. And as I mentioned to you, the energy cost of the equipment to reduce and to treat the emissions is very high, but in industrial environment, you are used to. The point is that the small polymers 3D printers are used, for instance, in private house or in very small centers in which those characteristics are not taken care of. So we have not to say we should take care also of the toxicity of the process. So we should have printers that are confident, we should have filters to treat the emissions and so on. Yes, I will share the slides. Please share the contents, please. Maybe I can send the slides by mail to Professor Vishwesh Badeka, or
Sure, sir.
to other or to any other people that you may require. Just send me a mail and I will send back all the materials used today, and I will also share some other materials that can be useful. And also shared my both mail addresses, the university one and the personal one.
Right, sir. Sir, I think we can very well approach the closure for this session. Thank you once again, sir. It was a really wonderful session. And from the entire team, I, of course, would like to thank you. And for the concluding remarks, I would like to invite Professor Vishwesh Badeka. Sir, please.
Yeah, good evening, everyone. And so, success of any talk depends on the participation of the uh, delegates and their active participation. I mean, both the talks were very, very informative, very much knowledgeable, and the kind of the questions were asked by all the participants were very, 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 I mean, good. I really thank both the speaker, Dr. Vivek Patel. He delivered a talk on friction stir welding and its sustainability, and Dr. Antelino Asteria also for delivering a talk on manufacturing and its sustainability aspects. It was really wonderful that manufacturing processes are produced. I mean, the maximum energy consumed by the manufacturing uh, domain compared to the construction and the agriculture and other domain, as you mentioned.
Yeah.
And we being, we from the energy university, and we always look into that how we can integrate the energy and the manufacturing. So probably here there is a connect that energy consumption and the manufacturing, they are there is a good linkage between both of them. So on behalf of organizing committee, I still remembered. Anyways, Dr. Patel is have been to means he was with us for a long period of time, and I still remember with Professor Esteria, we had a GYAN program at LD College of Engineering long back, and probably he came to PDU. He delivered a talk also on friction stir welding. So that was the initial interaction that we had with the professor. So, without taking much of your time, I, on behalf of the organizing committee, on behalf of the Department of Mechanical Engineering, Department of Mathematics, and special thanks to Dr. Kunal Mehta for chairing the session during this second day of faculty development program. We have two more, this program is there till Saturday. Two more sessions are lined up tomorrow. One from again Atira, Dr. Ankush. He'll be delivering a talk on composite and Industry 4.0, its integration. And another speaker is from Space Application Center, Ahmedabad. So once again, thank you everyone, and thank you for joining this AICT sponsored faculty development program. And special thanks to both the speakers also. Thank you.
So thank you
Thank you,
for
sir. Sir, I request all the participants to please switch on their video so that we can click on the common photograph.
okay. So
So,
thank you
Professor,
for
when are you visiting next?
I don't know. I don't know, but I am really, really eager to have the chance again to visit you because I visited your university 2 or 3 times, and each time was very fruitful interaction. So I hope to have the chance as soon as possible. So I hope soon. And thank you again for giving me the chance to have this presentation. Uh, and sorry for not wearing a tie, but today is Christmas, so I am in my mother house because for Christmas the tradition is to go to your grandparents or parents' house and celebrate all together. So I don't have the tie. So sorry for
That's
not
okay.
wearing
That's
the
okay.
tie.
It's okay.
So we have similar traditions at Diwali.
Yeah,
Uh,
I
we
know, I know.
also we also go to our parents and grandparents' house.
I had the chance to spend a Diwali in India a couple of years back in Ahmedabad.
Correct,
Okay.
sir. Correct, sir. Fine.
Okay,
So
I
I
think
think with this we can end this session.
yes, yes.
Thank you once again, everyone, for joining this session. Thank you. Have a good night and a
Thank you
Merry
Thank
again.
you.
Christmas ahead. Thank
Thank
you.
you.
Yeah. Thank you. Good
Bye
night.
bye.
Bye.
Bye, sir.